All right. So, lesson 1-3, evaluating limits analytically. So, what we were doing last time is we're using the table like here that we're going to do in the kickoff, but we were also using the graphs and that official definition of what a limit is. So, today, kickoff, let's start there. Then we're going to get into actually being able to calculate what that is using the equations we have. So, right here. So, we're looking for the limit as x is approaching, so if we look at our x values, we're approaching 1 of our function. We don't know what our function is exactly, but this is what it's going towards. So we're looking here. As we get closer and closer to x, what are we doing with the y's? Well, we're getting closer and closer to 3. So that's going to be the limit. So keep in mind, limit is what we are approaching with the y value. So what is our graph doing as we get close to that x? So first thing we're going to look at is, well, just simply direct substitution. First step we should always do is look, can we put in that x and solve for it? So, because that value may exist. Now, we're going to get into a little later what happens when it doesn't exist, but to start off, what happens when it exists? Well, we have our theorem 1-1 here, which I'm going to use the examples below here to help me with that. But starting off, what this is saying is, as we approach an x, if we just have a number here, the limit will be that number. So for limit as we approach 2 of our function 3, it's just going to be 3. It's going to be whatever that number is. If we have a variable, it's going to be whatever that x we're approaching. So as x approaches -4 of x, we're going to be at -4. Again, it's whatever that x is when we have just one variable. If we have a variable raised to a power, it's whatever we're approaching that x to that power. So here, as x approaches 2 of x squared, 2 squared is 4, and that is our limit. So, with these theorems, they're not necessarily theorems that you would think of back to, say, geometry, where we use them to prove things. These are pretty much just stating this is how you go about doing it when you have it like this. So if we have a number, it's that number. If we have a single variable, it's that whatever x is approaching. If it's to an exponent, then it's whatever x is approaching raised to that exponent. So, as far as some properties go, if we have these two limits, so the limit of our function f is going to be our limit L, and our function g, that limit's going to be the letter k. So how this will work is this. If we have a scalar multiple, so if something is times that function, it's the limit of the function times that number, whatever that multiple is. Some difference, if we're adding or subtracting functions, it's their limits added together or subtracted. If we're multiplied, we multiply the limits. If we divide the limits. Now, keep in mind that limit of k can't be 0 because that'll end up being bad. So our limit of g of x. Okay? And lastly, if it's raised to a power. Any function raised to a power, it's whatever the function's limit raised to that power. So this is what they're talking about. If we have this one for an example. Technically, we could split this up and go the limit as x approaches, looks like 2, of our first one of 4x squared. Plus the limit as x approaches 2 of 3. So x squared is really our function of what's going on. So if we're going to 2, if we put 2 into there, we know we take 2 squared and get 4. This 4 is a scalar multiple. So whatever our function is, take it times this. So if their function was 4, we take it times the 4 out front, and we have an actual limit of 16 for that first one. This last one, we know the limit is whatever the number is if there's no variable. So we'd add the limit in, which is 3. So sum or difference tells us, hey, just find the limit of each one, add them together, and we get 19. Now, we could simply just go, okay, as x approaches 2, we put that 2 in for x. 2 squared is 4. 4 times 4 is 16, plus 3 gives us our 19. So think what those properties are is what allows us to do each one. We know if it's an x squared, we just take whatever our x is approaching, square it. We're going to multiply whatever multiples in front, add it to any other function that we have. In this case, it's just a 3. So that limit's going to be 3. Add them together, we get our 19, and we're done. So, limits of polynomial functions and rational functions. If we have a polynomial, so a multiple termed function, if you think of it that way, it's just going to be put that in for every x. Whatever x is approaching, put it in for every x. Same thing when we have a rational. So if we have a fraction here, put it in for the top, whatever that polynomial is, put it in for the bottom, whatever that polynomial is, for every x, and what you get out is going to be our solution. So like this. We're going to put one in for everyone on the top. So 1 squared is 1 plus x of 1 plus our 2. On the bottom we'd have x of 1, so 1 plus 1. So 1, 2, 3, 4. 1, 2, which ends up being 2 then for our overall limit. So plug it right in for every x on the top, every x on the bottom. When we have square roots, you're simply going to plug it into that square root, and whatever c is, and that's kind of a typo here, this should be a c, whatever that root of c is, we're there. We also get into composites. So what this is going to do is we're going to find the limit of the inside function first, and then what that limit is goes in for the outside function. So find the limit of the inside first. Whatever that limit is, we put it into the outside function, and we get her. So here it's already split up, but what function they're talking about is the limit as x goes to 0 of the square root of x squared plus 4. So if we put 0 into here, 0 squared is 0 plus 4, we get 4 for our limit. So notice that's what they're putting in for the x of the next one. So square root of 4 would end up being 2. We can do the same thing keeping it all together, but we do that again, the inside part first. So 0 in there, 0 squared is 0, 0 plus 4 is 4, the square root of 4 gives us 2. So again, as we go, we don't necessarily have to split this up. We can do it all as the whole. But keep in mind you do the inside part first, then the outside with composite. Always build inside to outside. As far as the trig functions go, this is where we're going to use that unit circle. So if this is 0, this would be pi over 2. This here would be pi. This would be 3 pi over 2. So our values here, we would be at 1 comma 0. We would be at 0 comma 1, negative 1 comma 0, and 0 comma negative 1. Now you might be going, why do we need that? Well, its sine is the y, cosine is the x. So if we're doing sine of x, so x being whatever our angle is, so say it's pi over 2, we come here to sine at pi over 2 is the y is 1, that's what that value is. Okay? So these are how these tie together. Remember, sine is the y, cosine is the x, tangent, so let me go y, x, tangent would be y over x. Cotangent here is going to be x over y. Cosecant would be 1 over the y because cosecant sides with sine. Secant goes with cosine, so this would be 1 over our x. So here we have one. Our limit is going to be of x, cosine of x as x approaches infinity. Or not infinity, pi, sorry. So we're going to plug those in for those x's. So what we're going to get is pi times cosine times pi. Or cosine of pi, sorry. So cosine is our x, and we're looking at pi. So at pi, our x is a negative 1. So in here, we'd get negative 1 for that value. The pi would be times it on the outside, so negative 1 times pi leaves us with the negative pi for our limit. Now, so far, sorry, and I was off the screen. So again, x, pi goes in for x, pi goes in for the x here. Cosine of pi is negative 1 when we look at our graph, times that pi, so negative pi. Now, so far, everything, we've just been able to plug it in and we've gotten an answer. So that value exists at that x. Well, what starts happening when we don't have that x? Well, first thing we're going to try to do is try to find an equivalent equation, an equivalent function, so that we can plug that into x and still find it. So can we manipulate this, which is going to involve factoring this out? So this up top here is really a difference of squares, or difference of cubes, because 1 cubed is still 1. Difference of cubes goes like this. So when they are subtracted, so that's a difference, how they factor out is a minus b times a squared plus ab plus b squared. When they're added together, it's going to go to a plus b, a squared minus ab plus b squared. These are from advanced math. We covered them then. You probably don't remember them, so make sure you write these down on your notes. And save these for quizzes and the test when you put it on your note card. So this top one is going to go to the limit as x approaches 1 of, so x is being cubed, 1 is being cubed, so we're going to follow the top one since it's minus, of x minus 1 times x squared plus 1 times x, which is x, plus 1 squared, which is still 1. And our bottom we know is x minus 1. So think back, this one doesn't work because if we put 1 in, 1 minus 1 is 0. So that's why we're going to factor the top. And now we can cancel that factor out. And when we put our 1 in, we get 1 squared, which is 1, plus 1 plus our 1. So our limit ends up being 3. All right? So when you're finding these limits, again, first thing, always see if you can do direct substitution. Sub that x, what x is approaching in for every x, see if you can solve that out. If it doesn't work, then see if you can do it with an equivalent function that matches what the function we have. Okay. Lastly, we can apply theorem 1.7 to include anything analytically that. So if that function is the equivalent function, then we know their limits are the same. So we can put it into that other limit. We may also use a graph or a table if we can't quite tell for sure. We can always go to that. So finding the limit of this value. Well, the limit as x approaches negative 3, we put that on the bottom. Negative 3 and 3 make 0. That's bad. So we can factor the top. Bottom will be x plus 3. Top will go to x plus 3, x minus 2. So again, 3 is positive because we got a positive middle. So the bigger number is positive. Now we can cancel these x plus 3's out. And so if we put a negative 3 in here, negative 3 minus 2. So let me write this out. The limit as x goes to negative 3 of x minus 2, negative 3 in there, leaves us with a negative 5. Okay. So what we've had on these last two here is we can't tell if there's a limit with how it is. That is called indeterminate form. So if we cannot be found with the form that we have, it's called indeterminate form. What we're going to try to do is make it into a determinate form by factoring it out usually. All right, so this one here, we can't necessarily put 0 in. However, we could rationalize this by timesing it by its conjugate. So the square root of x plus 1 minus, or plus 1, because it's a conjugate, over the square root of x plus 1 plus 1. Well, up top, we would FOIL it, but the middles are going to cancel, so we'd have the limit of the first two, which would just be x plus 1, because the square roots would cancel, times 1, which would be plus the square root of x plus 1. On the bottom, x would be times this here. So we would have x parentheses, the square root of x plus 1 plus 1. So if we distribute our x in, we would get, well, again, this was limit as x approaches 0. Wait, what am I doing? This is not this. this should, well, it would cancel because we're going to do 1 times 1. There we go. So this should be a minus 1 on top, which will cancel. That's where we're going with that. So right now we have the limit of our top, which is x, as x approaches 0, of x parentheses the square root of x plus 1 plus 1. These x's can then cancel out, leaving a 1 on top. So when we put a 0 in now, so the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. When we put 0 in there, 0 plus 1 would be 1. The square root of 1 is 1. So we're getting 1 over 1 plus 1, which ends up being 1 over 2. And that's it. Now, we're not going to necessarily do this one per se, but something to keep in mind is this squeeze theorem. Really what we're doing is we can't factor it out and make it work. We can't rationalize it to make it work. So what we're going to do is we're going to pick a function that's bigger than it and a function that's less than it. And we're going to show that at our point, both of those functions are going to be the same thing. So if ours is in between those, ours has to be that as well. So we pick one bigger. That's going to go to this value. We pick one smaller. That one's going to go to that value. So ours in the middle has to go to that value as well. Reason why I bring that up is this next part is proven by the squeeze theorem, which are these two limits. If we have the limit of, as x goes to 0, of sine of x over x, it's going to be 1. And if we have the limit as x approaches 0 of 1 minus cosine of x over x, it's going to be 0. It's proven using the squeeze theorem here, picking one that's bigger than ours, picking one that's smaller than ours. Therefore, ours in the middle has to be it. And the proof is all here if you want to check it out. But we're not going to worry about that right now. We're going to go ahead and solve these and get these figured out. So, starting with find the limit of tangent of x over x as x approaches 0. Well, let's see if we can break this up a little bit. Tangent, if you think back to advanced math, tangent of x, there's an identity, it's not a reciprocal identity, but a quotient identity, where tangent of x is equal to the sine of x over the cosine of x. And that's what's going to get subbed in here. So the limit as x approaches 0 of, and I'm going to make this 1 over x for the bottom. Tangent is going to become sine x over cosine x. From there, we're going to rearrange these a little bit. So the limit as x goes to 0, sine I'm going to put over the x. So these are interchangeable, so I can switch these two numbers around. We're multiplying, so multiplying is commutative. So we're going to have limit of sine x over x times 1 over cosine x. So sine of 0, the limit of sine of 0 of sine x over x, we just did with this here special trigonometric limit. So as x goes to 0, the limit of sine x over x is going to be 1. So we can substitute 1 in for that first one. 1 over cosine, that's where that unit circle comes in. At 0, we're at 1 comma 0. And again, cosine comma sine is our ordered pair. So cosine at 0 is going to be 1. So that value is 1 as well. So therefore our limit is, well, 1. Now, when it doesn't quite match up, this is something we can keep in mind. We need to make whatever this is the same as what's on the bottom. So to make this a 4x, we could take the bottom times 4. If we take the bottom times 4, we're going to take the top times 4. So what we're going to have here is the limit as x goes to 0 of 4 sine of 4x over 4x. So if we look at just this part, now that part matches what's inside here, what's on the bottom. So this is technically the limit as x goes to 0 of 4 times the sine of y over y. So I'm going to let y be 4x. So now that matches. That matches this trig function. So this back part, when we find the limit, is going to be 1 times the 4 in front of it, and so we end up with 4 as our limit. And that is it. That is this lesson. So let me know if you have any questions. Please send me a message if you're having trouble. Otherwise, until next time, we'll talk to you later.